Welcome to the Invisible Ink experiment, brought to you by the ACS Singapore Chapter. Photoresponsive chemicals modify their properties upon light exposure. This specific colorless molecule, depicted on the left, undergoes an internal rearrangement when exposed to UV light. This process includes forming a new carbon-carbon bond, resulting in the transformation into the yellow-colored molecule shown on the right. Exposure to white light destabilizes this newly formed carbon-carbon bond, reverting the molecule to its original state. By developing various derivatives, a range of differently colored molecules can be synthesized. These molecules are soluble in a polar organic solvent called tetrahydrofuran, or shortly, THF. We are interested in incorporating photoresponsive molecules into a polymer network while this network is being formed. The network of choice is cross-linked polydimethylsiloxane, or as shortly called PDMS, which has excellent optical, electrical, and mechanical properties. During the formation of the polymer network, we swiftly disperse photoresponsive molecules throughout. Gentle heating then speeds up the network's development while also eliminating solvent residues. These photoresponsive dyes become an integral part of the polymer matrix. On exposure to UV light, the dyes transform to a colored state, and under white light, they revert to colorless. This dynamic change creates intelligent materials that respond to light stimuli. This experiment showcases how such materials can be prepared in a chemical laboratory. Before we start our experiment, prioritizing safety is crucial. Protecting your skin and eyes is essential. Ensure you're equipped with the necessary personal protective equipment, PPE. Wear closed shoes and leg coverings, tie up long hair, and don't forget your lab coat, goggles, and gloves for complete protection. Also, ensure good lab ventilation, especially when handling volatile solvents like THF. We start our experiment by precisely measuring the chemicals. First, we balance an empty vial. Next, we add 50 milligrams of photochromic dye to this vial and document the exact weight for precision. To create the PDMS network, we mix 3.75 grams of Part A with 0.375 grams of Part B. Part A, the main component, is a viscous liquid containing the base silicone elastomer. As you can see, Part A is a really viscous liquid. Once we've measured and recorded the weight of Part A, we tare the balance, resetting it to 0, ready to accurately measure Part B. Part B, the cross-linker or curing agent, when combined with Part A, triggers the curing process, transforming the mixture into a solid PDMS structure. Luckily, this process is slow at room temperature. We return to our bench to dissolve the dye in 1.6 milliliters of THF. We'll start by precisely measuring the THF in a volumetric cylinder, then carefully pour it into the vial containing the dye. After sealing the vial with a cap, we'll gently shake it to ensure the dye fully dissolves. Now we combine our dissolved dye with the forming PDM's polymer. Given the viscosity of the PDMS polymer, we'll employ vortex mixing to ensure thorough integration of the dye into the polymer. After the dye and the polymer got well mixed, we poured them into a disposable aluminium pan. We then place the aluminium pan in the lab oven, setting it at 60 degrees Celsius for 2 hours. This duration and temperature are ideal for the polymer to cure properly and for the solvent to evaporate completely. After 2 hours, our dye-functionalized PDMS network is ready. We remove the aluminium pan, and as you can observe, the elastomer exhibits excellent mechanical and optical properties. It remains both strong and transparent. Now, we'll expose our dye-functionalized polymer to UV light for 10 seconds. For this demonstration, we've prepared a mask made of paper foil with the ACS letters cut out. This mask will enable UV light to pass through the letters, illustrating the effect. Wow, our photochromic dye has been activated by the light, turning a vibrant yellow. While the contrast against the white background isn't strong, it clearly demonstrates the principle in action. Let's examine the blue dye, which is highly sensitive to UV light. Even minimal exposure passing through the paper mask can activate it. And now we have 3 different dye-functionalized polymer networks exposed to UV light for 10 seconds. Wow, these colors are stunning. And the best part is that they're fully rewritable. This video demonstration was developed by the members of the ACS Singapore Chapter and the NUS ACS Student Chapter. If you found this demonstration engaging and informative, we invite you to learn more about our activities and join our community. Simply follow the QR code on your screen to visit the ACS Singapore Chapter's page. Thank you for watching.